What is dark matter and dark energy? Do they have the same kind of relationship that the physics, no matter, and energy have? That's what we're going to talk about today. There are two things called dark matter and dark energy. They sound similar, but they're not the same thing. I think that's something like 95% of what's out there. We can't see it. It doesn't interact with ordinary matter, so we don't know what it's made of. We only know that it exists because of its gravitational pull. And for dark energy, we only know that it exists at all because it makes the expansion of the universe speed up. The idea is that ordinary matter is only a small part of the mass of the universe, but we think it's some kind of particle. We call it dark matter. The idea is that the expansion of the universe is accelerating because of something called dark energy. So we gave these names to these things which we cannot see directly, and we use those names to describe what we observe in the sky. If you look at how galaxies rotate, you find that they rotate faster than they should if you take into account only the matter that we can see. And then you say, well, maybe there's more matter around, but you can't see it because it doesn't emit light or anything like that. You can't see it. But because it has gravity, it pulls on the galaxies and makes them rotate faster than they should. That's the idea of dark matter. And for dark energy, you look at distant supernova and you find that the light from those supernova is shifted towards the red. Which means that the universe must be expanding faster now than it was when the light started traveling. If that's the case, it means that there must be some kind of energy that fills the universe and pushes everything apart. This is Einstein's general relativity. Spacetime tells matter how to move, and matter tells spacetime how to curve. When spacetime curves, that's what we call gravity. Now, what does this have to do with energy? Well, if you look at the equivalence principle, which is one of the cornerstones of Einstein's theories, you find that energy and mass are equivalent. This is why nuclear energy can be so deadly, because a little bit of mass goes into energy times c squared, and that's an enormous amount of energy. And the equivalence principle says that the gravitational pull of a mass is the same as the gravitational pull of the energy that has the same mass. So, if you have a ball on a string and you rotate it around your head, that ball has a gravitational pull towards you. And if you imagine that the ball is emitting light, then the light also has a gravitational pull towards you. This is why light bends around massive objects. The light has an energy, and the energy has a gravitational pull. So, the question is now, do these two dark things have the same relation that energy and matter have? Well, the reason that we even ask this question is that the word energy in the name dark energy sounds like it has something to do with energy. However, the dark energy could very well just be another form of matter. If you go back to the days when Newton developed his theory of gravity, he had no idea what energy was. He didn't even know about special relativity. And in his mind, there were only two types of matter. One was like a ball that you could kick around. It was something solid. And the other was fluid. So, if you think that dark energy is some kind of fluid, then it could very well be that it has the same gravitational pull per unit mass that ordinary matter has. In that case, you could rename dark energy to dark matter and nobody would notice any difference. The reason we do that is that the word dark energy has been used in astrophysics since the 1930s, long before it became fashionable to talk about dark energy. And dark matter was first introduced in the 1930s by Fritz Zwicky, who actually used the term dark matter. It's really confusing because he used it to mean something entirely different from what astrophysicists mean today. But that's what the word means, and that's what we'll stick to. So when people talk about dark energy today, they usually assume that it's not some kind of matter, but rather that it has something to do with energy. And that's why I think it's a good idea to rename it to dark matter. Then we could say that dark matter has the usual gravitational pull that we expect from matter, but that dark energy has no gravitational pull at all. Then it would also make sense to introduce the concept of negative mass, which is what I talked about in my earlier episode about negative mass. If you have negative mass, then the thing with the negative mass will accelerate away from any other kind of mass. And that could explain why the expansion of the universe accelerates. But you might say, hold on, isn't energy supposed to have a gravitational pull? Yes, that's right. But you have to remember that energy comes in many different types. There's kinetic energy, potential energy, internal energy, and so on. If you have a box full of gas, then the gas molecules inside the box have kinetic energy. This kinetic energy has a gravitational pull. But if you put a brick on top of the box, then you've increased the potential energy in the system because the brick could fall. This potential energy doesn't have a gravitational pull. In fact, the potential energy has the opposite gravitational pull as the kinetic energy. So the total gravitational pull of the box with the gas and the brick on top is 0. If you believe that the total energy of the universe is 0, then this means that the energy that has a positive gravitational pull must come with a type of energy that has a negative gravitational pull. For example, if you stretch a rubber band, you increase the potential energy of the rubber band, and that will slow down the motion of the molecules in the rubber band. So the molecules move slower, so they have less kinetic energy. So if you stretch a rubber band, some of the potential energy that you put in will always end up as heat in the So the total energy that you put in goes partly into making the molecules in the rubber band move faster, and partly it goes into making the molecules in the environment move faster. So if you believe that the total energy of the universe is 0, then the energy that goes into the rubber band will have a positive gravitational pull, whereas the energy that goes into the environment will have a negative gravitational pull. So if you look at the total gravitational pull of the rubber band, you get 0. It's basically the same argument that Richard Feynman used to argue that antimatter should have a negative gravitational pull. Richard Feynman was one of the developers of quantum electrodynamics and one of the most brilliant physicists of the 20th century. I made an entire episode about him, which you can watch here. So if you believe that the total energy of the universe is 0, then it's perfectly possible that the dark energy could have a negative gravitational pull. And if it has a negative gravitational pull, then it will accelerate away from all other kinds of matter. And that could be the explanation for the accelerated expansion of the universe. However, this is just speculation. What we know for sure is that whatever it is, it doesn't have the same properties as the energy that we know. Otherwise, we would have noticed it long ago. And that's why I think it's a good idea to give it a new name. Let's call it dark matter. This is a new episode with a slightly different format. I hope you like it. Please, let me know in the comments what you think. And if you want to support what I'm doing, you can check out my support page or become a member of my channel. Dark matter is one of the topics that we cover in my course on astrophysics. It's a beginner's course that you can take without any background knowledge. It'll introduce you to the most important concepts in astrophysics, such as black holes, neutron stars, the Big Bang, and the expansion of the universe. And afterwards, you can continue learning more about your favorite topics in science, computer science, or maths. All courses on Brilliant come with interactive visualizations and follow-up questions. Thanks for watching. See you next time.